another video in this series, the envelope on a synthesizer was a demonstration of the mathematical concept of a function. In this video, we will discuss another function, the oscillator. An oscillator on a synthesizer can produce a sound that has a pitch, known as frequency, volume, known as amplitude, and can also produce different timbres at that same pitch. Timbre can be thought of as a characteristic of a sound. If a piano plays a note and then a person sings the same note, they will have different characteristics. These characteristics come in different waveforms on an oscillator: sine, triangle, saw, and square. For the sake of this video, we will keep the volume the same for each waveform to just compare their timbre and to see how the functions can be used. First, the sine wave. The sine wave is the most familiar to math students as we see it in a trigonometry class. It is periodic, which means that the waveform repeats, and also means that one cycle or copy of the graph occurs in a particular period of time, we'll say is p. The period is related to the frequency through a simple relation. The frequency is the reciprocal of the period. So if a particular sine wave has a period p, then it has frequency f, which is equal to 1 over p. The timbre of the sine wave is the simplest, as it just produces one frequency, the fundamental. You can see this represented as one bar in the frequency analyzer. Sine waves are great for adding vibrato to a sound by modulating the pitch. In this application, the modulating sine wave has a low frequency, and if the amplitude is changed, it increases or decreases the amount of modulation. The next waveform is the triangle wave. The triangle wave is similar to the sine wave. Imagine just having a sharp point at the top and bottom where the curves are in the sine wave. The period and frequency relate in the same way as in the sine wave, and in fact this is true for all of the waveforms. The timbre of the triangle wave has the fundamental, but also a couple of other frequencies above the fundamental. These extra frequencies are called harmonics. The harmonics on the triangle wave are odd, meaning that they are odd number multiples of the fundamental. If the fundamental frequency is 220 Hz, then the harmonics in the triangle wave are 220 times 3, which is 660, 220 times 5, which is 1100, 220 times 7, which is 1540, etc. The frequency 220 Hz is an A on a piano, and these harmonics are close to other keys higher up on the piano. However, if we look at the triangle wave on the frequency analyzer, we can see that the harmonics have lower bars. This means that they are occurring at lower amplitudes than the fundamental. Triangle waves are also good for adding vibrato since they are similar to sine waves. In another video, we discuss how a triangle wave is the integral of a square wave, and one can be shaped into the other by the use of filters. Next is the saw wave. The saw wave is the most harmonically rich of the waveforms, as it contains even and odd harmonics. So if we take our same 220 Hz from before, but now analyze the saw wave, we'll see we have harmonics of 440, 660, 880, 1100, 1320, etc. And similar to the triangle wave, as the harmonic frequencies increase, their amplitudes decrease. Because of their rich timbres, they are a great source for creating a variety of sounds on a synthesizer. Some oscillators have a saw wave that has the diagonal edge going down and to the right, whereas others have the diagonal going up and to the right. We can relate these to linear functions with either a positive or negative slope, and at low frequencies they modulate things like pitch or volume in a vastly different way than what we heard with the triangle or sine wave. And finally, the square wave. The square wave has odd harmonics like the triangle wave, but the higher harmonics don't drop in amplitude as dramatically as the triangle wave. In this way, it is a better source for sound creation than the triangle wave, but will sound hollow when compared to the saw wave. The square wave has a shape that has a horizontal edge at the top and the bottom of the graph. This is a perfect visualization for essentially on or off. Because of this, square waves are great for sending out what are called gate signals. These gate signals on a synthesizer can trigger events on or off, like sequencer steps, individual sounds starting or stopping, etc. Square waves are also great for amplitude modulation to have the volume change from loudest to quietest, which is sometimes called tremolo on guitar amplifiers. Each of these functions can be used in a variety of ways for sound creation. Saw waves are good to synthesize brass or string sounds, while square waves are good for bass or horn sounds. We can also add the waves together through a mixer and create other waveforms. This is the same idea as adding two functions and getting a new function. We can also compose the functions and multiply the functions, and in doing so, one function is changing something about the other. We see this again in vibrato, tremolo, and other sorts of modulation. Here are some examples for the kind of sounds that synthesizers can make.
If we got married, would that be cool?
Finally, these oscillators show up in more places than just synthesizers. Since they can produce functions that are periodic, they are great for things like clocks, computers, and radio transmission.